Stokes' theorem. This theorem sucks. But it is sort of like an extension of Green's theorem. So Green's theorem allowed us to do circulation of two-dimensional vector fields. Stokes' theorem is circulation of three-dimensional vector fields. There's the preliminaries. S is an oriented surface with parameterization G, which is serving as a function from some domain D onto the surface. Right, D is a domain in the plane bounded by smooth, simple, closed curves, just like Green's theorem. G is one-to-one and regular, except possibly on partial D, the boundary of D. Let F be a three-dimensional vector field, so it has three component functions. Each component is continuously differentiable on an open region containing our surface. Then the circulation along the boundary of the surface of F dot dr is the flux integral of the curl of F. Circulation is defined relative to the boundary orientation. So what do we mean by boundary orientation? The orientation of a boundary of a surface. How lovely. To why OneNote does this. See, just to consider a hemisphere. Oh, well, let's do it in green. So to differentiate. That would be the boundary of our surface of the hemisphere. The orientation of that boundary is the direction you'd have to walk on it, such that when you extend your right hand, it points in the same direction as the normal vectors.
Scroll up back to the
Could I? Yes. Do I feel like it? That's a whole nother question. No, you didn't do it right. Just do it. Shine. All right, so if we have outward pointing normal vectors here, you'd have to imagine yourself now walking the boundary. What direction would you have to walk so that your right hand was always pointing outwards? Well, for this, it'd be counterclockwise. Inward pointing would be clockwise. That's the orientation of the boundary. It sucks. There's no easier way to determine it other than to imagine yourself walking on it.
again.
So that's the direction you have to walk so that your right arm, when extended, points in the same direction as the normal vector. So if it's outward pointing, you'd have to have your arm pointing out of the surface. So whatever direction that is, that's the orientation of the boundary. Right, in the case of a hemisphere, counterclockwise for outward pointing, clockwise for inward pointing. Keep in mind that Stokes' theorem also works in reverse. If you're asked to find the flux of the curl of a vector field over an open surface, you can also evaluate it as a circulation. It does work both ways. Personally speaking, I would rather just calculate a line integral than do flux. So in actual applications, I very rarely ever use Stokes' theorem. The problem with the other direction is you have to know it's a curl field first. And then you have to know what field is it the curl of in order to evaluate the flux as a line. So again, even that's not really too useful. We're going to verify Stokes' theorem for this vector field and the boundary of the upper hemisphere of x squared plus y squared plus z squared equals 1. Starting with the line integral. A curve serves as the boundary of the upper hemisphere of x squared plus y squared plus z squared equals 1. Well, that boundary is the unit circle on the xy plane. Right, so that is parameterized by cosine theta, sine theta, 0. Assume positive orientation, so counterclockwise, 0 to 2 pi. Now, circulation along that boundary, integral from 0 to 2 pi, evaluate f along the parameterization. Oh, wait, what am I doing? It's times z squared. Now, dotted with r prime. Plus sine squared, sorry. That first term's going to evaluate out to 0. Right, doesn't matter if you choose u to be cosine or sine. You're still integrating over one full period, which is automatically 0.
Same thing you did with the we put the parameterization in the.
No, that's because z was 0.
Oh.
Right. Because it happens to be on the xy plane, that's why z is 0. Use the reduction identity for sine. 1/2 minus 1/2 cosine of 2 theta. 1/2 of cosine of 2 theta is going to evaluate out to 0 because you're integrating over 2 full periods of it. You're left with pi.
And integrals in general. So I know the equation that we got originally is like lowercase f r times the magnitude of.
That is if you're integrating a scalar function. This is a vector field. So there's two different, right? So for both line integrals and surface integrals, you have two different. You can do it with, you can integrate a scalar, which is generally easier, or you can integrate a vector field. These three theorems only deal with vector fields. So that's why it's this way. It's essentially the same thing, right? Except now it's dotted with dr instead of times the magnitude of dr. Yes, I set it up that way on purpose. I think I set it up where there should have been 10 questions.
Yeah.
5 should have been scalar, 5 should have been vector fields. I think I did the same thing with surface integrals. 5 should be scalar, 5 should be vector fields. But you're asking why it was a different formula, I take it. Yeah, that's why. Flux integral, the surface integral. We need to parameterize the surface. Well, it's just the parameterization S of 1. Remember, that's cosine theta sine phi, sine theta sine phi, cosine phi. Since we're dealing with the upper hemisphere, theta goes 0 to 2 pi, phi goes 0 to pi over 2. This gives us a normal vector of sine phi times S of 1. Now we have to evaluate curl. Yeah, and thankfully this curl is very nice. Partial y, negative 2yz. Partial z, negative 2yz. First component 0. Partial z is 0. Partial x is 0. Second component is 0. Partial x is 0. Partial y is negative 1. The third component is 1. Which is just k hat. Curl of f evaluated along the parameterization is still just k hat. Dotted with sine of phi times S1 dA. Integral from 0 to 2 pi, integral 0 to pi over 2. We only want the z component of S1, which is just cosine phi. So this is what our flux integral becomes. That is going to be pi times sine squared of phi, or negative pi times cosine squared of phi. Either one, they give you the same answer. In either case, that evaluates out to 1 times pi, which is just pi. And Stokes' theorem has been verified.
The normal vector.
That is known for a sphere. It's always a squared sine of phi times the parameterization for the unit sphere. All right, A is the radius, so in this case, 1. Line integral is easier. And it usually is. We'd have to have a very complicated boundary with a simple surface in order to make Stokes' theorem actually worth it. And to be perfectly honest, I can't think of a simple surface with a complicated boundary. Any simple boundary is going to have a simple surface. Any complicated boundary is probably going to have a complicated surface. So you're probably just better off doing the line integral, to be perfectly honest.
We continue to do like the line integral and the other integral. And then we get the same answer. If we were to not get the same answer, then either it would mean that some of the conditions for Stokes theorem.
Two possibilities. Either Stokes' theorem does not apply, or you did something wrong. If you know for certain that the conditions of Stokes' theorem applies, then you just did something wrong. We verified Stokes' theorem. The two integrals are the same.
Okay.
That's all we were asked to do. Question is, how much further into Stokes' theorem do I want to get? Answer not too far. Rename this. D5 and 26. Divergence theorem. Possibly my favorite of the three. Let S be the boundary of some region in R3W. Yes. S needs to be piecewise smooth, oriented in the positive direction. In other words, outward pointing normal vectors. If F is a vector field with continuously differentiable components, I should say partial differentiable, but whatever. In an open domain containing W, then the flux of F through S, and remember that just simply means that our surface is closed. It's simply the triple integral of the over the region of the divergence of F. There is not a single scenario where the flux integral is simpler than the triple integral. I love this theorem. As long as your surface is closed, you can evaluate the flux as a triple integral. Yeah, let's just call this number 2. Verify divergence theorem. Let's first calculate the flux integral. So the region is bounded by x squared plus y squared equals 4, z equals 0, and z equals 3. The surface we're dealing with is a cylinder. And has radius 2. All right, so it's a cylinder of radius 2 that extends from z equals 0 to z equals 3. Since we're dealing with the closed surface, don't we have 3 surfaces that we have to consider? We have the top, we have the bottom, and then we have the side, the actual cylindrical part itself. For the top, well, the top is a circle at height 3. Should be too difficult to see that the normal vectors are k hat.
That's because it's just going straight up, right? Okay.
You cannot treat this as just k hat. Because R changes. R is not constant. So the magnitude of this normal vector actually depends on where on the circle you're located. Right at the center, you don't have one. As you move away from the center, the normal vector starts to get longer. I'm going to do the bottom next because it's also fairly easy. It's the same exact thing, except we're now at a height of 0. And again, it should be fairly straightforward to see that your normal vector is negative RK hat. Now for the side. Well, if we're looking at the surface of the cylinder, of the actual, what do you call that? For lack of a better word, the side. It's going to have constant radius, isn't it? Because you're only dealing with the surface of it. Radius is fixed at 2 now. It's now the height that's going to change. Theta goes 0 to 2 pi, your height z goes from 0 to 3. Normal vector here, again, should be pretty easy to see. Two cosine theta, 2 sine theta, 0. Right? You shouldn't have any pointing in the z direction because you're on the side and it's pointing away. Right, so the total flux would be the sum of those three. I'm gonna call that dt for the top. We have to evaluate f at our parameterization. F is 4x, negative 2y squared, and z squared. All right, and then dotted with r k hat, which is nice because its first two components go to 0 when you take the dot product. You're left with 9r. You should recognize that as the area integral for a polar region. Right, r dr d theta is dA in polar. The circle of radius 2, isn't it? So it has area of 4 pi times that by 9. Oh, I only did one of them. Oops. Then I'm just going to do this. Change equal to a dot and go, okay. All right, so that was for the top surface. Bottom surface. It's going to be the same thing, isn't it? Except that becomes 0. And this should require no work whatsoever. That's 0. Oh, beautiful. Wow. What's that dot product?
Not entirely sure.
It's 0. Remember, you're only doing the k component
Oh, that's right.
because k hat is 0, 0, 1. So the whole thing just goes to 0. Right? Integral of 0 is just 0, so that's really nice. Now I have to deal with the side. Evaluate f at g. That's 8 cosine negative 8 sine squared z squared. Dot it with our normal vector, which is just 2 cosine 2 sine 0. In this scenario, our z component now goes to 0. This part of it. We have no z. So that inner integral is just 3. Now we have to just try and figure that out. Well, cosine squared. Half plus a half cosine 2 theta. Sine cubed. Can write as sine times sine squared, which is 1 minus cosine squared. So sine times 1 minus cosine squared. Oh, that's beautiful. That whole thing evaluates out, or those last 2 terms will evaluate out to 0. Yay. That integral is just half of 2 pi, which is pi. Then times 48. What was the first one? Flux is 84 pi. Triple integral time. And you're gonna see why I love this theorem so much. So the region that is enclosed by our surface is just a cylindrical region. So why not use cylindrical coordinates? The set of points are theta z, so that r goes from 0 to 2, theta goes 0 to 2 pi, z goes 0 to 3. Divergence of f. Four minus 4y plus 2z. Since we're doing it as a cylindrical integral, write that in cylindrical coordinates. That middle term integrates to 0. Because r is not a function of theta. So I can just switch this order willy-nilly. Notice then there's nothing left for theta. Can integrate with respect to r. That'd be fairly simple to do because there's no r's. So the integral with respect to r is just 2. Integral of 4 with respect to z is just 4 times 3, 12. Z squared from 0 to 3 is 9. Yeah, 4 pi times 21. 84 pi. Now, it wasn't that much easier. Oh, I love divergence theorem. And so we verified divergence theorem. Two problems took an hour. I guess to be fair, I had to introduce the theorems too, so I'm still gonna say this took an hour. I'm gonna blame Stokes' theorem. I'm gonna say Stokes' theorem took up most of the time. Just because I hate Stokes. Here's what I think I'm going to do. Oops, I did not want to open my mail. I will just go ahead and post the Unit 4 test now. Let's make it do. The 27th, but I'll make it at the end of the day. Because normally I'd give you a week, but next Friday's reading review day. I'm not allowed to have tests due that day. So I'll just say, okay, it's due at the end of Thursday. Suck it, administration. I don't think there's a Stokes problem on here. Again, because I hate Stokes theorem and I don't want to write a solution for it. So you should be able to easily get through these. Tuesday, I will just continue to work on Stokes and divergence theorem problems. I'll probably just switch back and forth between the problem sets. Each one has 4. So I'll do a Stokes, then I'll do number 2 on divergence, then number 3, so on and so forth. I think I'll also make both of the final quizzes take home. I'll just create a form for them, post them on Teams. Don't know when I'm going to do that. I'll probably do that Monday. And then just have them done by, let's say, Thursday. Again, the final exam is going to be handed out next Thursday. Oops. I have not written it yet. I plan on doing that either this weekend or Monday. And I'm going to have a lot of fun writing it.
You were talking about having the final replace our lowest test grade.
Thinking about it. But the more I think about it, the more it just doesn't really seem worth it because the lowest test grade is only 5%.
I think it would be.
So it's actually not gonna,
Really,
it's not gonna bump you up as much as you think it is. It's only 5 quality points out of 100.
0 for one of the tests. I do something.
Right, but if you get 100, it's gonna boost you up by like 1 or 2,
You know,
depending on what the second lowest is. I still have to think about it. Of course, I would then say, if you turn your test in on time, you won't have to worry about the 0. But I mean, that's just me. Sick burn. All right, so let's go ahead and get that test posted. You should get an alert when I do post the quizzes. I'm going to warn you, the Stokes one, so number 24 is a doozy. Just because it's Stokes. I have decided I'm going to drop the 5 lowest quizzes. And just make 20 quizzes. Be an easy, so that's an easy 0.5% for each quiz. So I'll just take the top 20 quizzes. Look, I don't actually have to change the time this time. All right, it's going to take a while to do this. Before we leave, are there any questions about Stokes divergence, the little bit that we did? So same deal as last week. I'm going to head over to 3110 if you have quizzes you want to make up. Otherwise, I will see everyone again on Tuesday. So you have a choice to make because you submitted a quiz and the test.
Yeah.
And you only get one. So which one do you want?
Exam.
All right. So then you don't have a quiz to make up.
No, I do not.
I did print it just in case you wanted to, for some reason, you'd want to do the quiz instead of the test. So I'll email you with instructions on that later.
All right, perfect.
Don't know if it's gonna be today, because I have a lot going on today. If I get a chance to get on today, I will email today. Otherwise, expect that email Monday. But that will not affect, like, you can still put something in for next week. Right, so even if I don't approve it till next week, it still went in this week, so you can still put something in next week.
Okay. All right, yeah, no rush. I gotta work today anyway, so. Whenever you get a chance to send it.
At the latest Monday morning is when I'll go through them.
Thank you.
There we go, that's up there. I think you were next.
Then I also did.
And
I
then,
emailed you about the test, right? I figured you want to do the test over the quiz, so then
Okay.
that's going to be instead of the quiz.
Okay.
Because remember, we had that discussion in my office, so that's why I figured you'd do the test over the quiz.
Here's the silent sheet.
Oh, yeah, I was gonna forget. Thank you.
So you said for Thursday, you're gonna be giving the final.
Yes.
A couple weeks ago, like thinking something like this might happen, I'm not gonna be anywhere near New Jersey that Thursday. I have my best friend's wedding in which I'm the best man in South Carolina, technically North Carolina. But is it possible I can like get it emailed to me or anything?
I'm leery to email it simply because I'm going to use it again,
Okay,
and I don't want it floating around.
I get that. Could you
Um,
print it out beforehand?
You have to email me and remind me.
Okay,
Otherwise, I probably, even if I have printed out, I probably will not bring it on campus with me.
okay.
Because I don't plan on handing out. So you will have to email me to remind me.
To give it to me earlier?
Yes, I'll bring it on Tuesday.
Okay. Okay, thank you very much. I will be sure to do that.
You're gonna be here the Thursday of the final, right?
Yes, I will be able to come in and turn that in. Just that specific day, I'm not gonna be here. Thank you, Professor. Have a good one.